The only thing worse than giving the last talk of the day is giving the talk right after lunch. I'm sure more people are going to keep streaming in, and I'm going to do my best to keep you awake and alert. Fortunately, what we're going to talk about is, I think, in my opinion, a very interesting topic, and we're not going to focus too much on technology, although I will use the Azure Machine Learning Studio to do some demonstrations for you, but this is a very conceptual talk, and we're going to talk about data science and machine learning. So we're going to talk about what a data scientist is, what it does, and we're going to see some examples of machine learning in action in the Azure Machine Learning Studio. Does this work? No. All right. So let's start with this quote from Satya. It says, I believe over the next decade, computing will become even more ubiquitous and intelligence will become ambient. This will be made possible by an ever-growing network of connected devices, incredible computing capacity from the cloud, insights from big data, and intelligence from machine learning. Right? And I highlighted the last 3 lines because nowadays data science is about all 3 of those. Right? It's a combination of things coming together. First of all, the ability to move to the cloud, to be able to perform bigger computation, to be able to perform more computation, the ability to store almost unlimited amount of data, right? And the need to extract information out of that data. And you're going to hear sometimes the word insights, right? Or the word intelligence, right? Intelligence means being able to extract information out of it. What makes it insightful is the ability to deliver that information in a timely manner to the right people, right? And all of those are things that preoccupy data scientists. So what do data scientists do? Right? To a lot of companies, that can mean a different thing, right? A data scientist is not necessarily a particular role, and some would say it's even a buzzword, right? And in that sense, they'd be right. It's just not been clearly defined because every company sort of defines the role of a data scientist depending on their need, right? But I'm going to give you the short version, and then we're going to talk a little bit more about the longer version, right? So the short version is to start with some kind of business problem and to figure out a way to translate it into data, right? Anything ultimately can be turned into data. And what I mean by data is something that you can measure, right? So if you have an image, that doesn't look like data. But if you think of the way that a computer looks at an image, which is ultimately some kind of matrix, some kind of tabular data, or it could be multidimensional, some kind of array, right? That's data. So for us, it doesn't look like data. For a computer, it's data. And a data scientist is very much in that, occupied with that sort of thing, is how can we take all of these business questions and business problems, and especially the ones that seem very hazy, and turn them into a data problem. Then, once we have it as a data problem, we're going to find how we can use machine learning to find a solution. Now, a solution may not be a perfect solution. It may not be the exact answer to the problem we want, but it could be better than what we have to begin with, which could be intuition or just gut feeling or something that is not data-driven. And finally, the last piece is, now that we've figured out how we can take data and how we can apply machine learning to it, how can we surface that? How can we make that useful to our end users? Okay. So a while back, this Venn diagram was presented as sort of an example of what data science is all about. And in this diagram, you can see it as a combination of these 3 skills. One is, well, not necessarily a skill. It's a knowledge, math and stats. And that's really important because a lot of machine learning is really just statistics and matrix algebra. Then we have hacking skills. What we mean by that is not necessarily hacking into other people's computers, right? It's just the ability to program, right? Being a good programmer and knowing how to write programs for solving problems on our machines, right? And the last one is expertise, right? And this is a big deal too. It's just knowledge about our domain, knowledge about the field that we're in. If we combine the three of these, we get something close to what data science is really all about, right? Okay, sorry, I have a little typo in there, I guess. I'll have to fix that. But now we get to the long version of things, right? So let's start with business understanding. Right? We have a problem that we're trying to solve. We have a business question that we're trying to answer. And so we're going to make sure that we ask the right questions. We're going to make sure that we find a way to measure anything that right now is not measurable, right? And for that, I'll take you back to what Peter Drucker used to say. If you can't measure it, you can't improve it, right? So measurement and how it links to our original questions is very important. Once we do that, then we go and ask, well, do we have data, first of all? Do we have any data? Usually we have data, right? We may not have data that's immediately relevant to the question that we're trying to answer, but we have some form of data. So we're going to go and explore that data. We're going to ask if we can get more. We're going to ask if we can clean that data. We're going to ask how we can ingest that data, how we can build a data pipeline to do machine learning. Then we go to the part that a lot of data scientists like to spend most of their time on, which is the part where you actually do modeling, right? So you take the data, you process it. By processing, or the word is sometimes pre-processing, what I mean is that we have sort of data, the way that they're stored in databases and the way that they're stored in non-analytical environments, and we turn it into data that the machine learning algorithms can understand. Then we have what's called feature engineering. This means we have sort of the data as it is, and from that data we extract information in ways that makes the data more useful to the algorithms we're going to use. Then we move on to model building and evaluation, right? So we fit these models, we create machine learning models. We're going to look at some examples of that in our demo. And we evaluate them. We see if they're good, and we select a model that's going to work for us, right? Now, what's a model? What's a good model? What's a model that we should select? That used to be kind of not a very difficult question to answer. Usually you would say, well, the model that does the best at doing whatever it's supposed to do, which is usually predicting something, right? If you have a model and it's the best one at predicting, that's the one we're going to use. In the big data world, that's not the only consideration anymore. Nowadays, we're also concerned about, well, how fast is it? If it's a really good model at making predictions, but it's slow in the environment that I want to put it to use, and this could be a web application where it has to be very responsive, then maybe I should cut some corners. Maybe I should pick the model that is not as good, but it's much more efficient at computing. Right? So a lot of things go into that consideration as to what makes the right model. Right? One often quote by statisticians is that there is no such thing as a right model. Right? There are only useful models. We say all models are wrong, but some are useful. And so I would steer away as much as possible from the right and think more in terms of, is this model useful? Right? And that gets us to the next topic, which is deployment. Right? More and more data scientists are concerned about deployment. This is not necessarily the place for a lot of data scientists, including myself, where we feel like it's our element. It's something that we're trying to understand better. But what does it mean to take a model and to deploy it, to put it to use? And this could be a model that, for example, is running predictions on an ongoing basis and powering up an app, right? And what sorts of challenges do we run into in that kind of environment? And last but not least, iterate. This might seem like it's an exaggeration, but very often we get to our final product, we put it to use, and it just brings up more questions about our data, about what we know and what we don't know, about the whole process of doing data science. And so we go back to square one. This is a chart that I really like because it kind of puts the whole thing in a big picture. We're going to start at the top there where it says define the goal. Right? So we have a particular goal in mind. We have a business objective in mind. Our next step is to go to our data, to look at what kind of data we have and can we use it? Do we need to get more data and can we get it? Once we get data, we move on to building models. When we have a model that we we can go and evaluate it, right? And we can try multiple models and come up with the one that works for us. Then we go to presenting our results, documenting, right? Communicating. That's another big thing that data science is about. If we're really good at what we do, but we're not good at communicating these models, we're not good at explaining how they work and fitting our explanation to the audience, then we're not going to get very far with it, right? So presentation is really important. Finally, we move to the step of deploying the model. But notice that we have sort of a big kind of rotation going on the inside. But between each of these phases, we have also circles going back and forth, right? So as an example, you might have data, you might build a model, and your model may not be a very good model. And you're trying to understand why. So you explore the model and you realize, we had issues with the data that I was not aware of when I was just looking at the data. But now that the model is making predictions and those predictions are bad, I can go and see what is causing the predictions in some cases to be bad. And I can see that it goes back to some issues with the data. So we're going to go back and fix the data. We're going to go and improve our process. Same thing with deployment. And going back to defining the goal, right? We might put a model to use, make predictions, realize that this is a model that is making good predictions, but it's not scaling well, right? It's not necessarily a kind of model that we want to have in a production environment. And so we're going to go back and see, are we okay with the fact that we could have a model that makes slightly worse predictions? How much is this going to affect sort of the business goal of getting good predictions? But have a model that, on the other hand, we could put in a production environment and have it be very resilient. So we talked about kind of the data science process. Now we're going to zoom in on machine learning. Right? I say zoom in because when we talk about machine learning, we're really sort of like in the collect and manage data, build model, evaluate and critique model for the most part. To some extent, we might be in the deployment phase, right? But for the most part, machine learning is really just concerned about building models, evaluating those models, and also to some extent processing data in preparation for the modeling phase. So we're going to start by asking what machine learning is. Right? So machine learning is the ability to have an algorithm that takes in data and spits out explicit rules about relationships between the things in the data. Right? We want an algorithm that does our work for us. We're trying to understand what is going on in the data. What are the relationships? What are the associations? Are there patterns? Right? Can we predict this based on these other things? Right? And we don't want to go and figure it out, so we're going to use an algorithm that does it for us. Overall, machine learning can be divided into these two big groups, what we call supervised learning and unsupervised learning. So we're going to talk about the distinction between the two. Right? So supervised learning is really what we call a prediction problem. Right? If you're a statistician, you would say it's a prediction problem. A little bit later in the slides, I'll cover just some of the ways that statisticians and people in the machine learning communities talk about the same thing using a slightly different language, but there's a lot of overlap between the two fields. And sometimes it's good to know sort of what both terminologies are, because you hear people kind of throw them around based on their background. Right? So supervised learning is a prediction problem. Now we can be predicting a number, right? And that is what we call a regression problem. or we can be predicting a category, in which case we have a classification problem. Unsupervised learning is one of those things where, sometimes you might hear people refer to it as data mining. You might hear people refer to it as pattern recognition. Right? It's about finding structure in the data. We're not trying to predict anything. We don't have any particular column that we're interested in. We don't have a prediction column. We're just trying to find an overall structure in the data. Right? So we'll talk more about what that means. But let's begin with sort of defining some more terminology. Right? So as I said, in supervised learning, we do prediction. So that means that we must be predicting something. That something is what we call either a target or label. Right? We talk about label data. The label here are referring to that target, the thing that we're trying to predict. And then we have everything else that we're using to make predictions with, right? And those have all sorts of names. Sometimes people call them, the most common name is a feature, right? But you're going to hear sometimes people call them by other names, and I'll give you some more examples when we get to it. Supervised learning has one advantage. Once you predict something, if you know what the actual thing that you were supposed to predict was, then you have a prediction, and you have sort of what the prediction was supposed to be, or what it's supposed to come as close to as possible, right? And so you can evaluate these models really quickly. You can say, well, are the predictions getting pretty close to what they were supposed to predict, what we call the observations, right? Or the original values they were predicting. In unsupervised learning, we don't have anything like that. Right? We have unlabeled data, and we don't really have, if you think of the labels as the answers, the true answers. In unsupervised learning, we don't have a true answer that we can brush up against our predictions. In fact, we're not doing any predictions. We're just looking for structure in the data. And when we find that structure, we don't really have a way to evaluate them. Right? So in that sense, unsupervised learning is more hazy, more subjective, very difficult to interpret compared to supervised learning. Okay, so we talked about some kind of high-level concepts about machine learning. And now we're going to talk about the environment that I'm going to use for the labs. And sorry, I'm calling it labs. I should say demo. And the way that we're going to do this is, first of all, we're going to use the Azure Machine Learning environment. It's a really intuitive place to experiment and build models and to explore different models, compare different models with each other without having to, for the most part, you have the option if you want to, but for the most part, we don't have to write any programs, right? If we want to do anything more advanced, we can use R or Python to supplement what we're doing, but for the things that we're going to do in the demos I'm going to present today, that's not going to be necessary. With that said, this is what I want to do. I want to, first of all, take you to a demo so that you can look at the demo. And then after the demo, we'll go back and introduce the concepts in more slides. So usually you have the slides and then the demo afterwards. I want to do it the other way around. And I think this will be more intuitive because you'll actually be more familiar with what I'm talking about. It's not going to be as abstract when we talk about the concepts. Okay, so a machine learning experiment is basically what we're going to do. Usually you start from scratch. You drag and drop a bunch of things. I'm going to show you some examples, but for the most part, I've set up these experiments ahead of time in the interest of saving time and not having to wait for things to come together. Right? And we have two kinds of experiments. We have what's called a training experiment and a predictive experiment. I'll talk more about that when I actually have them, when I show them to you in the demo. I have some resources here for you that you can look at on your own time. Right? But let's now move on to our first demo of the day. So it's called regression demo. When you hear the word regression, think first of all that we're predicting something. It's a supervised learning algorithm. and the thing that we're predicting is a number. So I'm here in the Azure machine learning environment. When you log in, you get presented with sort of a page similar to the one I'm looking at. And I've created some experiments that I'm going to go to. And in this case, I'm going to start with linear regression automobile price. So this is what an experiment looks like. In Azure Machine Learning, we have this sort of canvas in the middle. When you start a raw experiment, the canvas is going to be empty. And then on the left side of the screen, we have all of these things that are called modules. Right? So I can type, for example, train model. And as I type, the modules narrow down until I get the single module, which is the one I'm looking for. And then I can drag and drop it into my canvas. It's really easy to lay out. As soon as you drag and drop it, you can see that because it's the one selected, it sort of has this blue outline, right? If I select anything else, notice that what changes is the right side of the screen. So each of these modules have some options associated with them. And you can change those options by selecting the module and by going to the left side of the screen. So I'm going to remove that. And as you can see, I've already laid an experiment together. The whole thing together is called an experiment. It usually starts with data at the top. And we do some things with that data. And then we build some kind of model. And if it's a training experiment, which is what this is, we end up evaluating the model and looking at some evaluation results at the bottom. So let's take a look at our data. This is a very interactive environment. So all of these modules, you can do a right click on it, and you're going to be presented with a set of options. And in this case, because I'm on the first module, which is the data, it would make sense for me to be able to visualize the data. So there is a visualize option. And if you click on that, you can come here and you can actually see the data. Right? So this data is a very small data set, only 200 rows, and we have 26 columns. It's data about cars. So each row is a particular car. We're going to know information about make, fuel type, aspiration, whatever that means. Some measurements about the size of the car. Again, not sure what bore and stroke are, but I'm sure they have something to do with the car. And you get to the last one, which is the price. So price might be interesting to us, right? Maybe we're trying to, maybe our business problem is basically we're trying to predict the price of a car based on information about the car, right? When we talk about these things we call targets in machine learning, right? Statisticians would call them a response variable. It usually means something of particular interest, right? Of all the things in the data, price might sort of have a special place for us because it's something that we don't always know, and it would be nice if we could predict it. Or maybe it's something that we're trying to estimate, right? The word for predicting in statistics is sometimes estimate, right? So maybe cars do have prices, but maybe we want to build a model, and the model is going to say if a car is overpriced or underpriced based on its estimate. Okay, so notice, by the way, that as you click on any of these columns, you can immediately see some summary statistics show up on the right side of the screen. And if you scroll down, you can see, in this case, what's called a histogram. So this is just showing the distribution of price. We can see that the majority of cars, if you think of like that second, well, let's just go all the way to right there. I think that's close to $17,000. Yeah. So $17,000. So the majority of cars are below $17,000. And cars that are very expensive are few and far in between. If we keep down, or if we keep price selected and we come here, there is a compare to option, and we can actually compare price with other things. So if I choose something that is numeric, such as mileage, what we get is a scatter plot. So it makes sense. The more efficient the car is, the more it should cost. So in that sense, this sort of negative kind of relationship, or relationship in the opposite sense, is shown in the scatter plot. If you keep it down on price, but choose a categorical column, such as, let's just do body style, right? We can see for each body style shown in the x-axis, the distribution of price in the y-axis. Okay. So we don't have too much time really to talk about statistics. I just wanted to show you kind of the interactivity of this environment. But we're going to go on to our next step. And what we're going to do next is just select a bunch of columns in the data. I've already done that, and you can see those columns listed here. I'm picking 4 columns out of the data: body style, horsepower, city mileage, or MPG, and the price. Okay. 3 of these columns are columns that are hopefully going to help me predict price. That's what in machine learning we would call features. And the 4th one, price itself, is my target. So assuming that I don't have anything else to do to clean the data, and most of the time we do. Most of the time data is not clean. There's a lot of work to be done before we're ready to move on to the modeling phase. But here I'm just going to assume that that's not the case, and we're just going to move straight to the next exercise, or the next challenge, which is building a model. So we come here. The first thing we have to do is we have to select a model. Right? Now, if you have enough experience doing machine learning, you would note that right off the bat, a couple of algorithms are just going to stand out. Right? The simplest algorithm we can build to predict a number is a linear regression algorithm. So we've selected linear regression there. And then we're going to come here, and we're going to train a model. Training a model is the fancy term for creating a model from data, right? We have a specific algorithm. It's called linear regression. Now we need data. The data is coming from the automobile price data. And combining those two, we can train the algorithm on the data. What comes out of that is something that doesn't look very, very charming, but it's basically what we call the regression weights. Statisticians call these coefficients, right? So it's basically a bunch of numbers that we can combine into an equation, right? It's not always the case that we have an equation, but for linear regression, it is the case. For most algorithms, it is the case. Now, this is what the equation looks like for us. Right? If we take those numbers, rearrange them a little bit, we end up with something that says, you want to predict price, start with negative 364, and then multiply whatever horsepower is by 156, add that or subtract that from whatever the mileage is, multiplied by 52, and then figure out which body type you have, right? Body type is a categorical column, so we don't really multiply by body type. We can't multiply by a categorical column, but we can say, find out which body type you have. Depending on which it is, that's the number you have to add or subtract. And what you end up with is a prediction. Now, obviously, for something like regression, putting together an algorithm or a little equation like that, when you have so few columns involved in the first place, not a big deal. But most algorithms are not that easy to interpret, right? And the equation itself, it might turn out to be something fairly complicated. And so we don't want to do that by hand. We don't want to hand type the equation after the model is built. And that's what Score Model does for us. It says, give me a model, give me data that you want me to predict on, and I'm going to go and do the predicting for you. Okay. In this case, the data that we're predicting on is the same data as the one that we use to build the model. Right? This is usually, by the way, a bad practice because your predictions are going to be a little bit biased towards the data that you use to make to build a model on. Right? But for now, it's gonna do for us. Right? So we can go back to our data, and we can see that now we have a new column in the data called scored labels. that's our prediction. So for the first row of the data, we have a convertible. We know the horsepower and mileage. We know that the actual price of this thing was about $14,000. And now we know that our model estimates that its price should have been about $18,000. Okay. So we have reality in the column called price. We have a prediction in the column called scored labels. And we can compare the two columns to get a sense of how well this model does. Right. Of course, we don't want to do it row by row. That would be pretty tedious. And so that's what this next module does for us. Evaluate model is going to go and run some statistics comparing the predictions to the observations. And what we get out of that is a bunch of different metrics. The one that is probably very common is this one right here. Right? And the way that we can interpret that number is that on average, we seem to be off in our predictions by about $4,000 or $4,300. Okay. Now, is this a good number? Is it a bad number? A statistician would be hard put to answer that. That's a business question, right? If you had to make a prediction, is business comfortable with being off by about that much on average, or is that too big of an error to be comfortable with? Another good number to think of.
It's not just business, right?
Yeah.
If you have a car that costs $13,000 and you have $4,000 error, that's a 30% error, right?
Yeah, I mean.
So I think that's also without knowing the business, right? For everything that you have, you want to have like maybe something like 5%.
Yeah, but.
Yeah, if you believe for 10 million cars. The car costs $30,000. They're not going to. Yeah, well, it doesn't matter, right? Car is going to be like a Bugatti. Yeah, but it wasn't $1 million car there, right? Doesn't matter. Doesn't matter. A different thing. What I'm trying to say, that's better. Not just a business.
Well, when I say a business decision.
That's also a machine learning, right? Measure it according to the. This is basically the accuracy of the model. Yeah, but like that doesn't. What I was trying to say is $4,000 out of the premium, not $4,000 out of the right. So that's something.
Okay, well, when I say business decision, right? When I say business decision, it doesn't necessarily mean business. It means it's a problem that mathematics cannot necessarily answer. The first thing we should be asking is, first of all, what are the predictions replacing? If before that we had nothing in place for making predictions, then even if you're off by $4,000, it's better than say using gut feeling to make an estimation. So business here is kind of a loose term. Now we got to move on. Sorry, but your point well taken.
Yeah, what I was trying to say, even in machine learning, you can normalize your error, right? 4,000.
Yes.
You can normalize the error. It's a common error.
Yes.
Then it does give you an absolute.
Yes, but it should always be taken with a grain of salt.
Yeah, agreed.
Right. Okay, so that's it. We have our example of regression, right? And now we're going to look at an example of classification. When we finish regression and classification, how are we doing on time, by the way? We have about, what? We're going to finish at 2:15? 7 minutes. Wow. Okay, we're probably not going to get to clustering, but we can finish classification. And then we'll review the concepts that we learned. Right. Okay, so let me just go and open up the classification experiment. And we are going to be classification right here. All right, so we've done things just slightly differently. Here we have the same data set, but if we go and look at columns to select, we've added a column there. And that column is the number of doors. I was looking for kind of a binary column meaning a column with two categories that would be kind of easy to play with. And this one kind of presented itself, right? Because thinking about cars, number of doors kind of also says something about the car, right? It says maybe it's more of a sports car, maybe it's more of a very efficient car, right? So it's not just about the number of doors in the car. It's kind of, are there things about that sort of speak to the car? And so we're going to use that as our example of what we're going to predict. Notice that price is in there, right? But we're not going to use it as a target anymore. We're going to use price as one of the things that might help us explain the number of doors in a car, right? That might help us predict it. And then the model that we're going to build in this case is a two-class logistic regression model. Well, I'm going to run this experiment. I've run it already, but I'll just do it again, just to kind of show you what happens when you run an experiment, right? And usually it's pretty efficient. So if you haven't made any changes, it's actually just going to give you the same thing back. If you made any changes at any of these nodes, it's going to basically keep everything as it was up to then, and then from that point on, it's going to rerun your code. Right. So we end up with an evaluation, and we can go and look at our evaluation. Before we do that, let me just go and show you the predictions. Right. So I'm going to go to score model, look at the data, and we can see that our predictions are right here. Right. So now we predict a category. It's the number of doors. There is the actual things, the reality that what we observe. So hopefully most of these match. If they don't match, we have what's called a misclassification. That is, we have one category that we see. Maybe it's a 4-door car, and our prediction is a 2-door car. And notice also that associated with the predictions, we have a probability. Right? So that's actually what happens under the hood, is this category classification problems turns into a estimation of probability problem. And if we want, we can use the probabilities, and in a lot of cases they could be more useful than the actual categories. The reason being that when you estimate a category, you have to put the cutoff somewhere, right? You have to say 50% or above probability is where I'm going to put the cutoff, or you could go higher, right? Anyway, we're going to go now to our evaluation, and this right here is called an ROC plot. We don't have time to really get into it, but one of the ways that we look at this plot is we take the area under the plot, and we call that AUC. And in this case, it's shown right here. And the closer that comes to 1, the better of a model we have. The closer it is to 50.5, the more the model resembles basically. The more it's not a good model, the more it's you may as well have flipped a coin. That's one way to look at it. Right? Another number to look at is this one called accuracy, right? And that says how many cases did you misclassify. Right? It's probably not the only good number to look at, because some misclassifications may cost us more than other kinds of misclassification, but it's a good aggregate number. Okay. So we looked at logistic regression. I'm going to get rid of this, and I'm going to choose a forest, two-class decision forest algorithm instead. So I got rid of one of my algorithms, and I dragged in another one from the modules. I'm going to connect it let me connect it to the train model, and here I'm going to select for the number of decision trees just 1. Right? So a decision forest is a tree-based algorithm, and as you can tell, a forest is really just a bunch of trees. Here we're just going to look at one of them. Okay. I shouldn't have to do anything else, so let me just run the experiment. Since I introduced a new algorithm, I'm going to have to retrain the model. So the first thing we should see is that the training is going to begin. As soon as we have a trained model, we can begin to make predictions. That's called scoring. And once the scores are available, we can evaluate the predictions by running the evaluate module. we go to our evaluation and we can see that our AUC is much higher, our accuracy is much higher, so we seem to have a better model. Right? In Azure Machine Learning, you can actually have two models and evaluate them side by side. You might have seen that there is a sort of little position there that's open. If you hold your mouse over it, it says scored data set to compare. Right? So we have the option of comparing multiple models in the same using or comparing two models using the evaluate model, but we're not going to have time for it here. Okay, so we're going to finish by just reviewing some of the concepts that we learned, right? And then since we began about 5 minutes late, I'm going to take the next 5 minutes, and maybe at the very end, I'll just show you a brief example of actually deploying this model, which is pretty easy in Azure Machine Learning. Okay. And what we're not going to have time to talk about is unsupervised learning, right? Clustering, I was going to show you the example for that, but we won't get to it. Okay, so just to review, right, we talked about our target. Right? If you are predicting something, that thing is called the target. There's different names for it. Target and response variable are the two main ones. The features or explanatory variables are whatever else you're using to predict the target. Okay. Now, I threw in a little caveat in there. My background is in stats, and regression in statistics doesn't necessarily mean predicting a number. Right? Machine learning people use regression to say predicting a number or algorithms that predict a number. Regression in statistics talks about sort of a family of models that give us an equation for the prediction, to put it in simple terms. Right, so, and you're going to hear people in machine learning use one or the other when they refer to it. So there's a lot of little things that cause confusion sometimes. But we have sort of different kinds of supervised learning algorithms, and you can see the most important ones here. The tree-based algorithms, of which we saw just one example, a decision tree. I didn't actually show you the tree, by the way, but we can go back to the experiment here, to our trained model, and I can visualize oops, looks like I have a problem here. Okay, we'll figure that out later. But we can actually visualize the tree. It's not always very helpful because trees can get pretty complex too. So we usually just build a tree and use it to make predictions. But for simple trees, there is a way to visualize it. Linear models, and we saw linear regression as an example, support vector machines and neural networks, including deep learning, right, are also examples of algorithms that are pretty common to use in supervised learning. Okay, we talked about what it means to train a model. Right? So you're going to hear people say, we trained the model. What they mean by that is that we chose an algorithm and chose a data set and fed the data set to the algorithm to create a model. Right? What comes out of that is what's called a trained model. Right? So the algorithm is sort of the raw thing. It doesn't have anything to do with the data. Once you apply it to the data, once you learn sort of the relationships and the rules and express them in trees or equations or whatnot, that's a trained model. A trained model can be used for scoring, as we saw. That means making predictions. Right? And once we have scores, and by the way, we can make predictions on data that's labeled or unlabeled. Right? If we don't know price, the model doesn't care that we don't know price. The model's job is to predict price. And what it needs to know in our case was body type and horsepower and such. Right? And it can give us predictions. But if we want to evaluate the model, the data that we make predictions on has to be labeled. We need to know the truth, the ground truth, so that we can compare the predictions to the truth. Okay. Regression has a bunch of metrics. We looked at the root mean squared. I was going to talk about R squared, but that's something that I've listed here. It's another useful metric to think of. Right? And then we saw an example of classification that was predicting categories. Right? And in our case, the category was two-door or car or four-door car. And for classification, probably the most useful thing to look at, especially for binary classification, is this thing called a confusion matrix, right? How many cases are there where something was positive? Right? Now, positive could mean 2-door or 4-door. You make your pick in this case. In some cases, positive is more clear. It could be someone has cancer. Something is an image of a dog. Right? And true or false is the reality. Positive, negative, that's what the model is predicting. Right? And so we compare them to see how many times we're right and how many times we're wrong. And in binary classification, you can see that if we're wrong, we can be wrong in two different ways. Right? And sometimes one is more important than the other. Okay. So we looked at the ROC curve and AUC. We talked about accuracy a little bit. Right? And this is sort of, if you want to kind of take everything that we did and summarize it, these are the big things that are important, right? A trained model, scoring a model, and evaluating a model are really the big things in supervised learning. Okay, I mentioned there was just one last slide, and I'll probably just leave it for you to go and look at on your own time, but just about kind of the different language that sometimes statisticians and machine learning or the statistician community and machine learning community can use when talking about the same thing. And even within the machine learning community, you can hear people use one term or the other. So it's just good to be familiar with that. Okay, so unsupervised learning, something that we're just going to skip for today, because I want to take you to just the last thing we're going to see today, which is taking a model that we have. In this case, we have a ready model that is going to predict whether a car has 2 doors or 4 doors, and deploying it. Usually, this is not a very straightforward thing to do, because this is when the data scientist has to go and figure out, first of all, what our deployment environment is. Is it powering up a dashboard? Is it something on the web? How responsive does it have to be? How well does it have to scale? How much data do we have in the production environment, and so on? But in Azure Machine Learning, it's actually pretty easy to set one of these up just for being able to test. And if you have a Azure account, you can go and you can actually purchase a plan that allows you to scale this web application that we're building. Right? So notice what happened is there was some rearrangement. Some of the things we did disappeared. Evaluating a model is not a thing anymore, right? We're not really interested in evaluating anymore. We've selected a model. We just want to deploy it. What I mean by deploy it is we want to make it power a web app that is going to go and make predictions. Okay? So evaluation has disappeared. The input is now some kind of web service input. The output is also a web service output. But our trained model has gone into this right here. We have a model that's a pre-trained model, right? And we can use it in the web app to make predictions. And the predictions are happening here in the score model phase. So now that we have this web app, I just have to run it to make sure that it's working, and then we can go and deploy it and look at what it's doing. Okay, so that finished, and now I click on the deploy button. And what I'm going to do is just show you sort of the newest interface. So there is it's in preview, but we get this sort of web page where we can, first of all, test our deployment to make sure that it's working, but also monitor it if we're actually going to roll this out. Okay, so we get presented with this little page here, and if you look at these, all of these are columns that were in the original data. Right? Most of them are columns that we didn't really use for the model, so we can probably ignore them. This is the column that we're trying to predict, right? So since we're trying to predict it, we can leave it blank. The ones that we did use are body style, if I remember correctly. Let me actually go back to the experiment and check that. Okay, so I'm going to return to the training experiment, and if I click on select columns, we are going to predict number of doors based on body style, horsepower, city, mileage, and price. And just to be able to give it some reasonable numbers, I'm going to look at some examples in the data. So for body style, I'm just going to say convertible. The next one is horsepower, and even though it's numeric, you can see that a lot of the numbers are the same, so it looks like this is what we would call a discrete numeric column. And I'm just going to choose 110 for horsepower. For city mileage, let me just do 18. That seems like a reasonable number. Okay. And then for price, I'm just going to say 20,000. You hit the request response button, and if you scroll to the top, there's the prediction coming back to us as a what's really just a JSON object, right? So now this JSON object can be picked up by any application. It doesn't necessarily have to be the web app that you have here, but this is one of the places where you can implement it. Okay, so we're going to skip a lot of that. Sorry about that, but I'm happy to stay behind and talk to you about more of this if you want. Any questions?
Neurons. Let's say you want to do like a long short-term memory neuron into like a deep neural network with a lot of hidden layers into an output like that.
Yeah.
Is that possible with the Azure infrastructure?
So we have a neural network module that you can play with.
With you mean the predefined ones that are there?
Yeah.
All right.
But deep learning is very computationally intensive, right? And nowadays, at least in practice, what people use is GPUs.
Yeah, exactly.
And because of that, you would ultimately have to change to some more programming interface for doing that, at least at this point.
Okay.
And that's why we have the CNTK library, for example, and that's just one way of doing it.
Okay, so what I think what I'm basically asking, is there a version of TensorFlow in Windows or in Azure?
Yeah.
Azure 2020.
Yeah.
So we'll.
2020.
Oh yeah, okay.
Yeah. Yeah. Well, we can talk more about that.
Okay, awesome.
Yeah.
Okay.
Any other questions? Okay. I have to be respectful of the next presenter because I am the next presenter.